We're going to continue to look at proof and disproof by counterexample. So this is example 198, and we're given the statement that if m and n are consecutive odd numbers, then at least one of m and n is a prime number. So we need to disprove this using a counterexample. So to do this, we're going to pick a couple of values of m and n until we find one that doesn't agree with this statement. So to begin with, we might pick m equals 5. Well, this one's definitely not going to work anyway in disproving this, because 5 is a prime number and n would be the next consecutive odd number, which is 7, which is also prime. So that agrees with the statement. So that's no good. So to give ourselves a chance of disproving this, we want to actually pick the first number, m, as a non-prime number. So I'm going to pick 9. But when I look for what n is 11. So that's no good because n is a prime number. So we still haven't managed to disprove this by a counterexample. So we're going to now try m equals 25. And we can see that if we pick the next one along, n is 27. And we've done it because neither of these are prime numbers. So we need to make a statement that neither are prime. So we've disproved the statement by using counterexample. Okay, so now I'm going to look at this one, which is example 199, which is a little bit more complicated. So we're given the statement that two inequalities. We're given that if P is greater than Q, then it's saying that 1 over P must be less than 1 over Q. So we've got to try and state a condition on P and Q so that this statement would be true. We're actually going to do it by looking for a condition where this isn't true, first of all. So we're going to look at a counterexample for this. So to begin with, I'm just going to try and get a feel of the numbers here. And I'm going to pick two numbers, P and Q. So pick nice simple numbers. We're going to say P is 2, Q is 1. And just have a look at what happens there. So we pick P is greater than Q, as in the first condition there. And let's have a look at what happens to 1 over P and 1 over Q. So we'll get, well, 1 over P is equal to a half, and that is, as it says here, less than 1 over Q, because 1 over Q is equal to just 1, because it's 1 divided by 1. So in that case, it was true. So I'm now going to try and find it. I'm looking for something which is going to make this not true. So I'm going to pick that P is equal to 1, and I'm going to pick that Q is equal to negative 1. So let's see what happens here. So we can see that 1 over P would equal just 1 over 1, which is 1. 1 divided by 1 being 1. And 1 over Q is 1 divided by negative 1, which is negative 1. So this time we've actually got that it's the other way around. It's greater than. So 1 being greater than negative 1. And that is a counterexample to this. So we found that this statement is disproved by counterexample when when Q is less than 0 and P is greater than 0. So if we want to find a condition for P and Q so that the statement is true, then we have to come up with something that's going to disallow this situation to occur, so that won't allow this counterexample to occur. So a condition that would not allow this counterexample to occur would be that both P and Q were positive. So a condition for this statement to be true is both P and Q are positive. So I could say greater than 0. And the reason I've said that, just to repeat myself, is that if P and Q are greater than 0, then we can't be in the territory where we've got this counterexample, because that would mean that Q couldn't be 0, couldn't be less than 0, whilst P being greater than 0. So the counterexample couldn't take place if we have this condition applied. And that's it.